Alrighty, howdy folks. Um, I am delighted to teach this class. I enjoy teaching, but trigonometry especially, I think it's a fascinating course. It's not very difficult, but very important. And one more thing before we head off to the actual thing is every lecture of mine, you will hear me say, howdy, folks. That's how I'm going to start. That's because I'm a country boy from Tennessee. No, I'm just kidding. I'm not a country boy from Tennessee. I'm from India. But I don't know. There's a big long story about why I say howdy. But just wanted to give you a heads up, you know. Every time you will hear this and you go, what the hell is he doing, man? Yeah, there are reasons for it. Okay, all right. Without much further ado, let's do this. If you notice, I'm starting with chapter 6, section 1. Chapter 6. If you look at the syllabus, it says you start with 5, 6, 7, and 8, I think. You start with 5, it says. But how come I'm starting with 6? Here is where I say, trust me, I'm a doctor. Yeah, by the way, yeah, I am a doctor. My PhD is in mechanical engineering. Okay? This order is really good. In fact, what I'm going to do is I'm going to switch between 6 and 5. So if you look at my notes, which I'm going to post, you will see that I have written something like chapters 5 and 6. In the sense I combined both of them, and I'll switch between sections as and when I need to. Okay, so there is an order which makes perfect logical sense that I have figured out for myself, which I want to pass on to you. Cool. All right, what's the first one? It's about angle measure. Okay, definition. Definition, angle. This is something that you really need to know. Just about in any class from now on, whether you're taking physics or whether you will take physics in the future or you take differential equations, no matter what class you take, even engineering classes, always absolutely be sure to understand what the definitions are. If possible, just memorize every definition with an understanding. The moment you do that, your understanding of the subject goes up by leaps and bounds. Okay, so definitions are very important. In mathematics, in addition to definitions, theorems, laws, those are also absolutely vital. So be sure to memorize them and understand them. Okay, if you do, you might ask, why, man? That's because if somebody asks you a question, you can always ask yourself, wait a minute, what's the definition of that? And then be able to think through the problem. Cool. So definition. What am I trying to define here? This whole concept called angle. What in the world is angle? Hey, that angle, you must have heard, that angle is 45 degrees. What do you mean by that? That frugal burgle is 45. If I said, what in the world is frugal burgle? The truth is, because English is a native language for you, you have heard the word angle. Why do you need to define? I already know what angle is. But then, if it is an absolutely new word that you have not ever experienced, then you will need a definition. And so, let's actually properly define what an angle is. Here is the idea. Okay, let me show the pictures. Here, definition I have given here, and I need the help of these two pictures. I know those pictures look a little involved. Let me explain everything in here. When we are trying to define angles, we need a concept of positive angle and negative angle. Okay. Now, angle theta angle theta is equal to angle AOB is the amount ray R1, the initial side, needs to be rotated to coincide with ray R2, the terminal side. That is the definition. What? Okay, what in the world is this talking about? First, let's say we have a ray R1. You remember what lines, rays, segments, those are the things that you learned in high school geography, not geometry. Geography? Where in the world did I get geography? Okay, geometry, high school geometry. I'm sorry about that. So we learned about rays. Ray is, it has one end point is clearly known. This is the end point. But on the other side, there is no end point. Okay, it just keeps on going. That arrow indicates that that ray keeps going that way. Even though we have stopped here, in reality, it just continues along the same direction. So we have a ray R1 and another ray R2. Okay. Now, and what we are trying to define is this, what is this angular measure? What is AOB, that angle we are trying to measure. And this angle is that theta, and the theta angle is the same as this AOB. Okay. Now, if you want to find out what that angle is, this is what apparently you need to do. This initial side R1, the initial ray, you need to rotate this. How much should you rotate? You rotate this so that it coincides with ray R2, which is called, the R2 is the terminal side. How much amount do you need to rotate R1 so that it coincides with R2? That is the angle between R1 and R2. Or that's the same as the angle AOB. And in turn, that is the same as theta. And what do I mean by positive angle? I mean, if the rotation is counterclockwise. What is counterclockwise? If you look at a clock face, and the way the seconds hand and the hour hand, the minute hand, they all move, they move in this direction, in a certain direction. That direction is called the clockwise direction. Now this arrow here, this angular arrow, shows that it actually is, we are talking about an opposite angle, opposite direction rather, right? So that is counterclockwise direction. If the angle is measured in a counterclockwise direction, mathematicians and engineers have decided, and physicists of course, have decided we will call that as a positive angle. Cool? All right. And now here we have negative angle. The concept is more or less the same. We have an initial side R1, a ray R1, and the terminal side ray R2. And if the question is, hey, what's the angle between ray 1 and ray 2, man? Then you'll say, well, how much do I need to rotate R1 so that it coincides with R2? Oh, you need to rotate it by this amount, theta. Oh, okay, so that angle is theta then. Yeah. But in which direction did I have to rotate R1? Oh, you had to rotate, I had to rotate that in a clockwise direction. Oh, that means the angle is negative. That's the whole idea. And then if you look at this statement I wrote, that is precisely what I said. If the rotation is in the counterclockwise direction, then the angle is considered positive. Now, what's up with this parenthesis clockwise and the parenthesis negative? Well, this is a trick many writers use in order to convey the information succinctly. The way you're supposed to read this is, if the rotation is in the counterclockwise, and then you ignore the clockwise, the parenthetical stuff. The rotation in the counterclockwise direction, the angle is considered positive. Ignore this parenthesis. And then you come back and read the same thing, but this time you say if the rotation is in the and you ignore the counterclockwise, is in the clockwise direction, then the angle is considered, ignore positive, negative, right? Clockwise goes with negative, counterclockwise goes with positive. That's the idea. Otherwise, how would I have to have written this? If the rotation is counterclockwise direction, then the angle is considered positive. And if the rotation is in the clockwise direction, the angle is considered negative. Right? So many extra words I would have to repeat. And this is a shortcut to that. That's the only idea. Cool. All right. You will see quite a few people adopt this strategy. So just getting you to know this. All right. Now, units of angle measure. Units. Let me tell you. I don't know if in high school people insisted or not. But once you come to college, and especially when you take chemistry or physics or engineering classes, people will pounce upon you to talk about units. What's the speed of that car, man? Well, it's 55. You get 0 credit. Yeah, it is going at 55. 55 what? 55 feet per second, 55 miles per second, or 55 miles per hour? Yeah, man, like 55 miles per hour. Yeah, why don't you say so? Right? So you are expected to give the units. If there are units to something, you better tell what the units are. And so, for this quantity angle, we do have units. Does anybody know what the units of angle are? There are 2 at least, there are 3, but at least 2 are more important. And they are radian and degrees. Right? Radians and degrees. The 2 important units of angle are degrees and radians. Okay. Now let's try to see what in the world these units are. For that, I need to digress a little and talk about something called circular arc length. What? You didn't even define what you said. You just said they are degrees. And what is the degree, man? Yeah. I know. Patience. Okay. First, I need to talk about what a circular arc length is, and then use that to talk about these degrees and radians. That's why I'm digressing like that. Cool. All right, circular arc length. Let's look at this. What is this? I took a part of a circle. There was a full circle with radius r. Okay. Here, I took only a part of that circle. And that curvy part, I want to know what the length of that curvy part is. That is actually called an arc of a circle, that curvy thing. And I want to know what the length of that arc is. That is, I want to know what the arc length is. And that is S. What do I mean by arc length? Think of it this way. Let's say you take a piece of string, and first the tip of the string you put at this bottom end of this arc, and then make sure that the other part of the string falls right on top of this circular arc. And when your string reaches that other end point, pinch it off. Cut your string off at that point. Now straighten that string up and see what that length is. That length is the arc length. Cool? All right. So if this is the arc length, S is the arc length, R is the radius of that circle or radius of the circular arc, then we can talk about the angle between these two things, or the angle subtended by the arc, right? That's a new word, subtended, meaning what the angle that the arc makes. Subtended is sort of synonymous with makes. The angle subtended by the arc, or angle that the arc makes at the center. Let's say that is theta. Cool. What now? A circular arc of length s is a part of a circle with radius r, and angle subtended at the center is theta. Okay, here theta is measured in radian. Let's say we measure this in that unit called radian. Then something happens. Then we have this wonderful relationship. The arc length is equal to the radius times theta. But for this to be true, what must happen is theta must be measured in radian. Cool? When you do, we have this simple relationship, is the basic point. Cool. With that, we can now define what a radian is. Okay. Look at this formula, and look at what question I'm asking. Observe that when S is equal to R, we have, what do we have? When S is equal to R, what happens to theta? Can you see? When S equals R, what should be the value of theta according to this? I don't know, man. Well, you do. Think about it. Because S equals R, can I replace this S with an R? On the left hand side I have a S. Can I replace it with an R? Yeah, because S equals R. Yes, you can. So that means we have R equals R theta. What am I asking? What is theta? Oh, okay. R equals R theta. What is theta? Divide both sides by R. So theta is equal to 1. R over R. Aha! So that means theta would be 1 radian when S is equal to R. Now, can you use this information to define what a radian is? When S is equal to R, theta equals 1. Rather, the other way around is also true. When theta equals 1 radian, S will equal R. So basically, 1 radian, an angle of 1 radian, is nothing but when the arc length is equal to the radius, whatever the angle subtended is, that is 1 radian. 1 radian is the angle subtended by an arc whose length is the same as the radius. That's the way we will define radian. So thus, a radian is the angle subtended by a circular arc whose length is the same as the radius. Cool? So now we have defined 1 radian. Now what about degrees? Okay, to define degrees, let's look at some things. This is what we just saw, right? We have a part of a circle, that is, we have an arc of a circle, and if the arc length happens to be 1 radian, if the arc length happens, sorry, I take that back. If the arc length happens to be 1 unit and the radius is also 1 unit, in that case, this angle is 1 radian. Okay, that's what we just saw. Cool. Now, what about this scenario? Now, our arc is not just a part of a circle, but this entire full circle. What is the arc length in the case? The radius is 1. I'm asking, what is the total arc length in this case? Hey, isn't that the same as the circumference of the circle? Yeah, it is. What's the formula for the circumference of a circle? 2 pi r. Pi d or 2 pi r. 2 pi times the radius, but radius is 1. So what's the circumference? 2 pi times 1, which is 2 pi. Oh, okay, so the arc length is 2 pi units, whatever units meaning. If the radius is 1 inch, then this arc length would be 2 pi inches. If the radius is 1 meter, the circumference or the arc length would be 2 pi meters, as simple as that. Okay, so in that case, when the arc length is 2 pi radian, full circle, did I say arc length is 2 pi radian? Sorry, 2 pi units, length units, then the angle subtended here is 2 pi radian. Are you with me, folks? We have a circle of radius 1, and so in this case, this arc length is 2 pi, and the angle subtended is actually 2 pi radian. Keep that in mind. And then, what if we were to have a semicircle, half of a circle? Oh, in that case, this angle subtended is going to be pi because the arc length happens to be half of 2 pi, which is pi. Why half of 2 pi? Because we are not taking the full circumference of the circle, and we are taking only half the circle, half the circumference of the circle. And so half the circumference of this circle with radius 1 is half of 2 pi, which is pi. Do you agree with that? Oh, okay. In that case, this means this angle subtended must be pi radian. Cool? One more thing I have. What if we have a quarter of a circle? Well, that means half of this semicircle, which would be an arc length of pi half, or circumference. You don't call it circumference, it's arc length of pi half. So that means this must be pi half radian. This angle subtended must be pi half radian. What? Angle subtended in this case is pi half radian? Yeah, but I thought this looks like a right angle, man. I know that's got to be 90 degrees. Very, very good. Give yourself a pat on the back. You are absolutely right. This angle, which I'm calling as pi half radian, is the same as 90 degrees. Oh, wait a minute. What about the angle inside a circle, the full circle? What is this angle equal to? Angle in a circle is 360 degrees, man. Yep, you are right. Why am I interested in that? Well, I'm interested in that because I want to know what degrees are, or what the relationship between radian and degrees are. So we have these options. You can say pi half radian is 90 degrees, and you would be right. Or 2 pi radian is equal to 360 degrees. Cool? So I'm going to use the angle subtended by a circle is 360 degrees concept, and I'll say, aha, so that means 2 pi radian is exactly the same as 360 degrees. Yes. Okay, so 1 radian is how much then? If 2 pi radian is 360 degrees, 1 radian is, well, divide both sides by 2 pi. So pi radian is 180 degrees. 1 radian is 180 over pi. I could have divided by. Anyway, either way is fine. Yeah, maybe it's advantageous to look at this way also. So 2 pi radian is 360 degrees, divided both sides by 2. So pi radian is 180 degrees. And so 1 radian is equal to 180 over pi. And this, I boxed it because you got to memorize this. 1 radian, 180 over pi degrees. Cool? And automatically what that means is we can go backwards. 1 degree equals how many radian? Well, if pi radian is 180 degrees, 1 degree equals how many radian? Divide both sides by 180. So you get right hand side, you get 1 degree, 180 degrees divided by 180 is just 1 degree. And on the left hand side, we get pi over 180 radian. So that's the relationship between degrees and radians. And here we have radians and degrees. You've got to memorize both these formulas. If you can recall this, if you can recall the figures and logically come to this, that's perfectly fine. But one way or the other, you must know these. Cool. All right, where do we go from here? We'll solve some silly problems. Convert 36 degrees to radian. Okay, blah, blah. Since 1 degree equals pi over 180 radian, how much should 36 degrees be? To me, the moment I see something like this, it's like 1 apple is 5 cents. What's the cost of 36 apples? 36 times 5. Right? I don't know what, I don't need to do it in my head. As a concept, 1 apple is 5 cents. 3 apples is 3 times 5. 7 apples is 7 times 5. 36 apples is 36 times 5. Same idea here. 1 degree is pi over 180 radian. 36 degrees is 36 times pi over 180. What is it? We'll figure out later. But as a concept, 36 degrees is equal to 36 degrees times pi over 180 radian. Now, the nerd that I am, I can clearly see that 36 goes 5 times into 180. Oh, wow. I don't know. I don't know the multiplication table for 36, man. Okay, that's fine. 9. Does 9 go into 36 and 180? Yep, 9 goes 4 times. 9 goes 20 times. 9 goes to 0, right? 20 times. So we have 4 and 20. Oh, 4 goes 1 times, 4 goes 5 times. So 1 over 5, pi over 5. That's so 36 degrees is equal to pi over 5 radian. But what is pi over 5? You can leave it as pi over 5. There may be some situations where you may need to know in decimals what it is. In that case, you'll have to come up with an approximate number for pi, 3.141592, blah, blah. And so divide that by 5, or 3.1416 is perfectly fine. Divided by 5, that many radian. Simple? Cool. Convert negative 30 degree to radian. Negative 30 degree? Does that make any sense? Negative 30 degrees. Well, what do you mean by a negative angle, man? Does negative angle make sense? Yes. See, initially that's what we talked about, right? An angle is considered positive if the rotation is counterclockwise. Angle is considered negative if the rotation is clockwise. So apparently we have a clockwise rotation by an amount of 30 degrees. And we are now being asked to find how many radian does that correspond to. Well, as simple as, again, same, since 1 degree equals pi over 180 radian, we have negative 30 degrees equals negative 30 degrees times pi over 180 radian, Okay. There's one more thing I want to show you here. A very useful thing. Please pay attention. Not difficult to understand, but something that you will pretty soon start doing. When you take physics or chemistry or a lot of engineering classes, you will need to do these kinds of multiplications and divisions and all that, where different kinds of units are involved. So at that time, absolutely be sure to keep on doing, writing the units, okay? In fact, this is, speaking of which, 1 degree is equal to pi, Pi over 180. The degrees have to cancel. So implicit in this is, in fact, how should I put it? One, how do I explain this? Yeah, that's okay. This is not a clear-cut example. The point I was trying to make is we are actually supposed to have a 180 degrees here, pi over 180 degrees, so that the degrees here will cancel with the degrees there, and we'll have 36 going into 180, giving us with just a 5. The degree and degree cancel, leaving us with a pi radian, pi over 5 radian rather. Okay. So the point I was trying to make was, you must keep writing the units also as you multiply. And this is somehow, yeah, cancellation of units. I should have done that. Okay. Sorry about that. Cool. Let's move on. Convert 3 pi over 4 radian to degree. Okay. Similar idea. 1 radian is 180 over pi degrees. So 3 pi over 4 radian would be 3 pi over 4 times 180 degree over pi. And so now pi and pi cancel. 4 goes into 180 45 times. 4 4s are 16. And you got a remainder of 2, 20. We will have 4 goes 5 times. So 45. So 3 times 4, 45. That is 135 degrees. Cool. Convert negative 13 pi over 12. Same idea. We have this. And so multiply by 180 over pi. Pi and pi cancel. 12. 12 goes 1 time. So we get 6 remainder. 60. 12 goes into 65 times. So this is when 180 over 12 is 15. So negative 13 times 15 degrees. When you multiply that, you get negative 195 degrees. Cool. Yeah. I usually don't let students use calculators. I want people to be able to do things, be macho. Who needs a stupid calculator, man? My brain is a better calculator than your stupid calculator. All right. What next? Coterminal angles. Whoa. Consider an angle measure of 30 degrees shown to the right. Okay. Would you agree this is about 30 degrees? I got, look at the positive rotation, the counterclockwise rotation also. Okay. What about this now? Ooh, what happens if we add 360 degrees to this? So we went 30 degrees. Now we are being asked to go a further 360 degrees. So that means we start here, go a full circle. Well, when we do that, where do we end up with? Oh, we end up back in the same place. Hey, we traverse a full circle and come back to the same place as 30 degrees. Is that a big deal? Yes, it is a big deal. That is, both 30 degrees and 30 degrees plus 360 degrees, which is 390 degrees, terminate at the same place. Can you guess as to, okay, what are we supposed to do and where did we end up with? I'm talking about coterminal angles, right? And now look at this. Terminate at the same place. Terminate, terminal, same place, right? Same termination. Coterminal. Yeah, that's the whole idea. So, when we add 360 degrees to a certain angle, we have a coterminal angle. Okay, now the question is, what happens if we add another 360? That means, let's start all over again. First we were here. We rotated 30 degrees. And then we said, hey, go a full 360. Head back to the same place. Now go another 360. Well, you still come back to the same place. So we can keep on going full circles. After you do a 30, you can keep on going any number of full circles and you keep ending at the same point. And that is exactly what we are talking about here. What happens if we add another 360 degrees? Or, in fact, any integer multiple of 360 degrees. See, that's the big interesting thing, is any integer multiple of 360 degrees we want to add. Okay, so let's do that. So that's the idea. Cool. We end up at the same place as 30 degrees, and so thus 30 degrees, 390 degrees, add a 360 to it, becomes 750. They are all called coterminal angles. Cool. Formally, now we need to define for an angle theta in the standard position. Okay, the angles theta plus n times 360 degrees, or theta plus, instead of 360 degrees, we'll say 2 pi radian. So that makes this n times 2 pi, or 2n pi. Theta plus 2n pi radian are coterminal angles. Where, what is n? N is an integer, which means what? That is, n is, whoa, what's this funny looking e, man? Well, that funny looking e is simply is an element of, or mathematicians shorten it to is in. Okay, n is in, or n is an element of this set. What is this set? This set contains the following elements: 0, 1, 2, 3, 4, 5, 6, so on. And also -1, -2, -3, and so on. Right? That is what an integer is. Integer n is an integer if it is one of these elements in this set. Cool. So that's coterminal angles. For the angle measure 50 degrees, find two positive angles and two negative angles that are coterminal. Isn't that simple? Coterminal angles are 50. First, I added 360, then I added 720 to get positive. Well, if we subtract a 360 and subtract a 720, we should have the same thing, right? We should get a coterminal angle, and I just added them up. That's it. Simple? I think so too. Cool. For the angle -pi4, find two positive. Okay. Which means we need to add 2 pi, 4 pi, and so on. 2 pi, 4 pi, 6 pi, 8 pi, or if you want negative angles, -2 pi, subtract a 2 pi, subtract a 4 pi, and so on, and work the fractions out, and you get 7 pi fourths, 15 pi fourths, negative and pi of all of this. Is this stuff really important? Do we need to know coterminal angles? Oh, you bet. In trigonometry, we are going to use this concept of coterminal angles big time. Okay, pretty soon we'll learn about something called trigonometric ratios, and there it matters that we are aware of what coterminal angles are. Okay, so this is an important concept. Be sure to work problems of this kind. All right, find the length S of the circular arc. Oh, do we know how to find the length of the circular arc? Yeah, we had a formula, didn't we? Does anybody remember what S is in terms of R and theta? Yeah, S equals R times theta, provided theta is in radian. Yep. S equals R theta, theta is in radian. And guess what? You just plug and chug and you're done. And we have R is 8 units and theta is pi fourth radian. Multiply them. S equals 2 pi. What? But that's not a full circle, man. How come this is the part that ended up being 2 pi? Isn't that the circumference of a circle? No, man. The circumference of a circle is 2 pi r. This is just 2 pi. Okay. All right. Find the length S of the circular arc. What? Look at how clever these guys are. They want us to find this circular arc length, but they didn't give the angle subtended by that arc. Instead, they gave the other one, the complement of it. How clever they are. Yeah, but we are equally clever, aren't we? Notice that the given angle is 140, but the arc points to the opposite side. Yep, it does. So we'll say, okay, so we can find the actual one. How? The full circle is 360 degrees. If we subtract this 140 degrees, we should get what our arc subtends. You agree with that? That was the whole idea behind this. And we do this and we get 220 degrees. Cool. We know the angle subtended. We know the radius. So we are ready to find S. So is it 5 times 220? Is the arc length 5 times 220? If you said yes, then nope. Theta must be in radian. So be absolutely sure to convert the 220 degrees to radian. Cool. And that makes this 11 pi over 9 radian. Now we are ready. S is equal to 5 times R times theta. 5 times 11 pi over 9 is 55 pi over 9. So far as I'm concerned, leave the answer like this, full credit. Okay. I don't know the stupid other softwares that you might use in order to do homework. They may have stuff in terms of decimals, and for that you may need to use a calculator. But if I'm doing a test or a quiz or something like that, you write your answer as 55 pi over 9, you're going to get full credit. Cool? All right. Whoa, what's this? Shucks. Area of a circular sector. Sector, meaning what's a sector? This pie, piece of pie, right? That is a sector of a circle. We want to find the area of a circular sector. How do we do that? I don't know. This was not supposed to show up right now. I goofed while setting appearance order. So please bear with me on that one. So I'm going to use the figures that I had before. If we have a full circle, would you agree that theta is 2 pi radian? Yeah, full circle area, the what do you call it? The angle subtended is 2 pi radian, right? Full circle, 360 degrees or 2 pi radian. And what's the area of the circle? Pi r square. Good old geometry formula. Okay, what if we had half a circle? In that case, the angle subtended is pi radian, right? Half of 2 pi, pi radian, and area of a semicircle is 1/2 of pi r square, right? Pi r square over 2. Okay, now if we go to a quarter of a circle, again, the angle subtended is pi over 2, and the area of that is pi r square over 4, 1/4 of pi r square, right? Half of the semicircle, or 1/4 of the full circle, so 1/4 of pi r square. Cool. There's something I'm trying to get to here. Now, what if it is some arbitrary theta? The angle subtended is some arbitrary theta. This one has a radius of r. Okay. So what would be the area here is the question. For that, what I'm wondering is, could we see a pattern in this and use that pattern to figure out the answer for our question? Okay, you may or may not have seen it, but if you've already seen the pattern and can come up with a formula, that is incredibly impressive. If you want to pause the video and say, wait a minute, man, you got a full circle, then for a half a circle you got this to be area, and for a quarter of a circle that to be the area. Let me see if you can come up with for an arbitrary angle theta. You are really smart. Cool. Let me see if I can help you in the process. When the angle here was 2 pi, when theta was 2 pi, did we get A to be 1 times pi r square? However, when the angle was pi, we have 1/2 of pi r square. When the angle is pi half, we have 1/4 of pi r square. Does that give you some kind of a pattern? Okay, when 2 pi, we have a 1. For pi, we have a 1/2. For pi half, we have 1/4. Well, if you didn't get that yet, no big deal. Don't worry about it. So, this 1, can I say 2 pi over 2 pi? Yeah. Here, can I say pi over 2 pi to get my 1/2? Right? Pi over 2 pi, yep, that is, pi's cancel and you get 1/2. Okay, how about pi half here? When I do pi half over 2 pi, do I get 1/4? Yeah. Hey, wait. Now I see a pattern. Every time in the denominator you have a 2 pi, man. Yep, you're right. What do we have on the top? 2 pi. What was the angle there? 2 pi. What's pi here? What's the angle here? Oh, that's theta. Theta is pi radian. What's the angle here? Pi half. So whatever is the theta, that goes on the top, and 2 pi in the bottom. That is the fraction of pi r square, which will give us the area. You see how clever that is? Mathematicians do that all the time. So, let me repeat. What is the area of any kind of sector? Whatever is the angle subtended divided by 2 pi times pi r square. Right? When the angle is some arbitrary theta, what should we say? Oh, okay. You don't have a specific number like pi half or pi, and you just have theta. Okay, I'll just replace this with a theta, man. Yes, you're right. Theta over 2 pi, right? Angle theta over 2 pi times pi r square. Theta over 2 r square. Right? That is the idea. So the angle of a sector is theta over 2 r square. Or people write this as 1/2 r square theta. Either way. If you forget the form, it's good to memorize it, but if you forget, you will always have a way of using your own intuition and pattern recognition to come up with the formula. Cool. All right. The top and bottom ends of a windshield wiper blade are 34-inch and 14-inch respectively from the pivot point. While in operation, the wiper sweeps through 135 degrees. Find the area swept by the blade. Ooh, isn't that interesting? What is this? This is the wiper blade. That wiper blade swings back and forth. And the bottom edge of it is here, and the top edge of it is here, of the wiper blade is here, and so it sweeps out this whole area. And the bottom edge is apparently 14 inches from the pivot point. Pivot point means it's fixed at that point, and all the other points rotate about that fixed point. And so that is 14 inches. Basically, that is nothing but the inner radius, and the outer point has a radius of 34 inches. The outer radius is 34 inch. And we need to find this area, the green one. Any thoughts on what to do? Yeah, find the area of this sector, the outer sector, minus the area of the inner sector. Area of sectors. Do we have any formulas for area of sector? We just did theta over 2 times r square. Do we know theta? Yeah, in both cases theta is 135 degrees, but theta should be in radian. Okay, we'll keep that in mind. We'll convert that degree to radian. Do we know r? Yeah, this outer radius is 34 inch, so we are in business. That's the whole idea. Area swept is area swept by outer edge minus area swept by inner edge minus. So radius of outer edge, we'll call it r sub o, and that is 34 inch. Radius of inner edge is r sub I, is 14 inches. Okay, look at how I'm writing step by step. This is the logical way of presenting things. A lot of times people just go, okay man, and just put numbers. And later when you look at your own work, you're like, what the hell did I do? You would have no idea what you just did. However, when you write steps like this, area swept is this minus that. Radius of outer edge is this. Area swept by the outer edge, and theta is equal to 135 degrees, is 3 pi over 4 radian. Angle swept. It's not area. I'm like, what the heck? Okay, angle swept by that, we need to convert into radian. So that's exactly what we did by multiplying by pi over 180. And angle swept by the inner edge is the same. And area swept is theta over 2 times r sub o square, 1/2 rad this one. And so when it comes to the units, okay, this turns out to be whatever this number is. When it comes to units, notice we have a radian here and we have an inch square here. Radian is actually a dimensionless quantity, which means you can think of radian as a number. It is actually a ratio of arc length over the radius thing. So multiplying by 1 radian is the same as multiplying by a number 1. Okay, and so inch square times radian will have a units of inch square, and that's what you see, square inches. Area swept by inner edge in a similar way, and I just subtracted the 2. Well, notice how I did. I didn't punch into calculator. Instead, I looked at this and I said, so 3 pi over 8 can be factored out. And 3 pi over 8, when factored out, we get 3 pi over 8 times 1156 minus 196. That's what I did. And so 3 pi over 8 times 960. And now I did 8 goes 120 times 3 is 360 pi inch square, and I didn't have to use a calculator. and I could leave everything in terms of pi. Cool? That's the idea. Whew. So we are done with this lesson, folks. I hope you liked it, and be sure to work on quite a few problems in this one. All right? Alrighty, see you later.